Hi everybody, I wanted to try something a little bit different for this video, so here we go. Today, let's talk about measurements and units. We'll also be talking a little bit about vector and scalar at the end of this video as well. So in terms of the objectives that we're looking for, especially for the IB, ladies and gents, we do have quite a few that we need to be paying attention to. In terms of what we're going to be really looking at throughout the year, there are lots of things we're going to revisit consistently. Expressing uncertainties in absolute and percentage, and talking about how errors are propagated or uncertainties are propagated is an essential topic of IB physics. In physics in general, IB, AP, doesn't matter. Error propagation is a huge fundamental part of science. Plotting our data with uncertainty bars and linearizing our data is also going to be an important factor in terms of our analysis. Okay, so I'm going to teach you some of those basic techniques right now in this video. So the essential questions that I want us to look at here, ladies and gents, are why is data collected and analyzed? How do I express a pattern to show a relationship? And how do people use data to influence others? So these are larger questions in terms of how we utilize the skills that we're going to learn. So let's start with measurement, ladies and gents. Measurement is the source of our error, okay? So what are the sources of measurement errors? There are lots of them. They can be flaws with the tool. They can be misuse of the tool by the person, the scientist. There can be design flaws in the lab, right? We have lots of different things, and each situation is unique. And this question, ladies and gents, is actually something that you'll be asking yourself after every single lab. What are the sources of measurement errors? Every good scientist reflects on this when they're done with their work, so the next person who undertakes it has a little bit clearer view of the path. We'll also talk about how we report error and how does what we measure affect how we measure, okay? If I wanted to measure the distance from Earth to the sun, I certainly couldn't use a meter stick to do that, okay? So we'll talk about some different techniques and the idea of measurement versus estimation. So let's start with a sticky situation. Here we've got an object, a ball that's bouncing up and down. We're gonna film this, but we wanna record the height of each bounce. So here we've taken a still shot of the object as we hope at the very top of its bounce. Maybe that's issue number one. But now we even have to talk about how we're going to measure the height of the bounce. And this is something that we have to choose for consistency. Do we choose the middle of the ball? How do we determine the exact middle of the ball for every time? Do we choose the bottom? Do we choose the top? These are really important factors that we have to make sure we're discussing and making sure they are explicit in our instruction. The more clear your procedure is, the less issues you're going to have. Let's look at another example. You have two measurement devices next to each other. You have to choose one in order to measure an object. Which is the best choice? Well, here you can see, ladies and gents, that one measurement device gives you very definitive markings while the other gives you half markings, right? This is a matter of precision, ladies and gents, and that's going to be one of your key vocab words for this chapter. When we are measuring something, the precision of the measurement device will dictate the precision of our measurement. If we are using a centimeter or meter stick that only measures in units of a half, that is the most accurate measurement that you can have, or the most precise measurement that you can have. Now, if that is the most precise measurement that you can have is half increments, maybe, perhaps, your data will not be very accurate. So we're going to talk about uncertainties now. Now, what you see here on the screen is not the type of uncertainty you will be dealing with just yet. We'll be talking about this type of uncertainty in year 2 as we talk about quantum mechanics and the Heisenberg uncertainty principle. For right now, I think it just looks cool. So when we're talking about uncertainties, ladies and gents, we really like to talk about two types of error, two sources of error. There is systematic error and there is random error. So what I want you to do, ladies and gents, I want you to take a moment, pause the video, and think about what the difference is between these two. When you unpause, the answer will be on the screen. So here we can see, ladies and gents, that systematic error has the same error with every data point. It is the same consistent issue with each data point. They are all to the left, right? Random error is just that. Each data point is experiencing a new interaction that's messing with the data. So we talk about this idea of accuracy and precision. Targets and darts are the perfect analogy for us to discuss accuracy versus precision and systematic versus random error. So going through this example right here, ladies and gents, we can really see and we can designate random versus systematic really easily, and where these lay on the spectrum of the two, because we can have a mixture of both random and systematic. Okay, so here we can see that we have low accuracy, low precision. This really does look like 100% pure random error. These targets or these darts are everywhere on the target. Here we have high precision, low accuracy. This is when we start talking about the systemic error. All of these data points are going to the same place. We're just not hitting the bullseye. Finally, high accuracy, low precision. This we would call, random error. And you can see here, ladies and gents, that if we were to compare these two, one has much more random error than the other, right? One is a little bit more accurate. So as we decrease the amount of randomness, we do get a more accurate answer, hopefully. And finally here, ladies and gents, we have something that is both precise and accurate. When you have a lab that is precise and accurate, you have very little error to deal with at all. So what does this look like graphically? I mean, we are in a science class after all. What is it going to look like? So here's a couple examples, ladies and gents. So the first one that we see to the left, we have random error, 100% pure random error. Now, how do we know that? If we look here on the right-hand side, the blue line is our true intake over time, and green is our sample average. So if blue is the target, okay, our average is very, very close to the target value. We're kind of accurate, right? Overall, if we average this out, it works. But our data is all over the place. So we experience lots of random error here. Looking at example number 2, we see something a little bit different, right? We see now our green and blue lines are completely separated from each other. Now, this is where we're seeing that systematic error. Okay? What that's showing us is that we are getting really precise results. All of our data is right on our sample line, but our entire sample is off. Okay? So what does it look like when we mix these two things together? Well, this is what it looks like right down here, ladies and gents. We can see that not only is our average value way off, but each of our data points is experiencing a random error. So here we want to do a practice problem, ladies and gents. I would like you to, for each of these, write down, is it random or systematic error? Is it precise or accurate, or both? Okay, answer both of those for me. When you unpause, the answers will be on the screen. So here you can see, ladies and gents, that each of these situations create something completely different. Some have very little error, some display no accuracy or precision whatsoever. So our job as scientists is to minimize this. And that's what a skill we are going to work on throughout the year. So let's start talking about how to calculate error, okay? It can get kind of confusing because there's 3 different types of error that's out there. You have what's called absolute error. You have fractional error. And then you have percentage error. Now, just to make things very, very clear, ladies and gents, fractional does not matter, okay? It is just a stepping stone from us to get from absolute to percentage. So just to make things very, very clear, let's go ahead and get started, all right? When uncertainty is given to us, it's generally given to us like this. Now, what you're seeing here is some type of quantity, something that's been measured, all right, plus or minus absolute error. In a second, I'll show you how to solve for absolute error when you're given a data set. But first, I want to show you how do we go from absolute error to percentage error. And what's the point of percentage error? Well, we use it to put on graphs. That's really one of the easiest things. It's easier for us to display when we talk about our data. Now, how do we get there? It's actually a really, really easy process. It's one equation. For us to go from absolute error to percent error or uncertainty, same thing, all we have to do is we take our absolute error divided by our quantity x times 100. If you take this, take the answer to this value, that is going to give you percent uncertainty. So in this case right here, if I have a 0.25 error and I have measured something that's 1.56, I get an error, a percent error value of 16. So when I plug this piece of data into data graphing software like Logger Pro, which we'll introduce next week, you put 16% in, it will automatically calculate the percent error for that data value and put it on your graph. So it's a really easy way for us to display information and manipulate it, especially with computers. Okay, there's a huge advantage to utilizing percent error. And it's a pretty easy process to get there. Okay, you can even type these calculations into your Excel worksheets and all your percent calculations are done. Okay, or Google Sheets, whatever you prefer to use. Now, real quick, we need to talk about something that's really important because calculating error, that's simple. All right, pretty much anybody can do that. Error propagation, that is a true elevated fundamental science technique. So what does that mean? Essentially, ladies and gents, if we have this quantity, x plus or minus our absolute uncertainty or error, what happens if I want to do x plus x? What happens if I want to do x minus x? What happens if I want to do x times x? X divided by x? Or what happens if I even want to raise x to a power? Well, here, ladies and gents, we have three separate rules that talk about each of these three situations, okay? When we are dealing with error propagation, all you need to do is remember these three rules, all right? Add or subtract, we add absolute uncertainties. If we multiply or divide, we add percent uncertainties. If we raise the object to a power or the quantity to a power, we take that power and we multiply it by our percent uncertainty. These are the three rules, ladies and gents, okay? So make sure you put this in your memory. It is in the data booklet, but this is a nice little tool for you to have in your back pocket. You will be using this for labs, okay? If your error does not propagate for your presentation, for your graph, you will not get full credit. So this is something we have to consider. So what I'd like to do now, ladies and gents, is I'd like to show you an opportunity of how this can be used with some very basic calculations, okay? So the first thing I want to do is I want to do a basic calculation of area. I drew a little rectangle. We've got length and width with their appropriate errors. So we know that to calculate area, I'm going to have to take 1.59 multiplied by 1.00. No problem. We know that's going to be 1.59. Easy peasy. Now the question is, what's going to happen with this area? How do we calculate the total uncertainty of the area that we're given? Really simple, ladies and gents. Each of these quantities needs to be turned into a percent error. So all we have to do is write out our equations just like this. And what you can even do, ladies and gents, what I think is the best thing about writing out your equations like this, as you calculate your percent uncertainties, all you have to do is add them together. So if we plug into our calculator, here we get an error of 0.6%. And here we get our error of 1%. That's all it takes, ladies and gents. Add these two things together, 1.6%. How do we find 1.6% of 1.59? Well, we can put 1.6% here, but maybe we want to display this as an absolute error. All you have to do is convert, ladies and gents. How do you find 1.6% of 1.59? Different ways to do it. I prefer to break 1.59 into 100 and then multiply by 1.6. Looks like we're going to get an error of 0.02544. Now, we've only got 3 significant figures here, so in reality, these 3 numbers don't matter. So our error did go up, right? It actually doubled itself in this case. So with this problem out of the way, I want to try one more, okay? Let's say we've got a car or bus, ambulance, whatever it is. It's on its way somewhere fast, all right? It's going to travel, let's say 150 meters, and it's going to make that journey in 3.1 seconds. Now my 150 meters, I'm measuring that with plus or minus 2 meters. My time, 3.1 seconds, I'm measuring that with plus or minus 0.1. So if I wanted to calculate the velocity of this object, the bus, car, ambulance, whatever it is, we know that velocity is meters per second. It is the distance traveled over time. So we've got to create that. We would have 150 divided by 3.1. Which gives us 48.38. Now, right away, ladies and gents, we have to obey our significant figures. You can see here that we have 2 significant figures for 3.1. We also have 2 sig figs for 150, but we're going to that first decimal spot. That is the most precise measurement we have. So that is as far as we can go. So what I'm going to do is I'm actually going to rearrange this to be 48.4 meters per second. But we still have this uncertainty we need to solve for. Okay, so we got to go through the process. We first have to calculate our percent uncertainties, then we can add them together. So 2 divided by 150 times 100, 0.1 divided by 3.1 times 100. We can get our answers. We'll add those together. Here we get 1.3%, and here we get 3.2%. What is our total? 4.52%. Again, we don't need that number because we're keeping everything nice and simple. 4.5%. And we have what is a pretty acceptable answer. But if remember, ladies and gents, when we really want to go all the way, we always make sure to take that percent uncertainty and we reapply it to our value. So I can go and calculate that 4.5% of 48.4 and we get 2.17, which we could do as 2.2 meters per second. This, ladies and gents, is going to be our final answer. So here we go, ladies and gents. We got our answers down. Let's actually move on to the last part of the assignment. It is curved data. So with curved data, ladies and gents, we want to try and take something curved and put it in a linear fashion. So really we have this equation right here. A is equal to, or the area of a circle is equal to pi r squared, right? So we have y is equal to some constant times x squared. We want to try and convert this to y is equal to mx plus b, that equation for a line. So there's a couple different ways we can do this, but I wanted to show you how we can go through it and really manipulate this data to give us the best piece of information. So here we have the same data that's already been linearized, and I want to show you the two different methods that we can use to go through that. So the first method, ladies and gents, is taking a is equal to pi r squared, and what we want to do is we want to somehow fix this equation. So we say y is equal to mx plus b. We know a is going to be on the y value. We know r is going to be our x value. And well, that would leave pi as our slope. So one easy way to do this, ladies and gents, is we could say a on the x, or I'm sorry, on the y-axis versus r squared on the x-axis. Really easy, right? All you had to do is draw y is equal to mx plus b and make those associations. Hey, if this is my y-axis, perfect. That means this is my x-axis, including its square value. So just by doing that, ladies and gents, we know that we can get a linear equation. And if you were to graph this, how could you check your work? Well, if you calculated the slope and it's equal to pi, boom, you got it, okay? Now that's one way to do it, ladies and gents. The next way to take a look at this is to actually manipulate the equation, okay? So a is equal to pi r squared. Another way of looking at this, ladies and gents, is you could easily take the square root of a is equal to pi r. If you were to graph the square root of a over r, you would also get a linear line. I know that for area, this particular method doesn't work very well, or it's a little bit more confusing, but for other equations, it works really, really well, okay? We can modify the equation, or we can convert it to y is equal to mx plus b, all right? Now, either way, ladies and gents, what you ultimately have to do is you have to take the results of your equation, and you either need to calculate that square root of area, or you need to calculate r squared, and it needs to be presented in your lab. The best part about this, ladies and gents, or what's most essential, is being able to recognize types of graphs. Okay, so here, ladies and gents, you can see three different types of graphs per row, 3 different rows. These are the main types of functions we should be familiar with. All right, I'm going to make one note on this page, ladies and gents, and it's about the identity or linear function. We like to say that this is directly proportional. Now, what that means, ladies and gents, it actually means a couple different things. It means that this is linear and goes through the origin. So make sure you know the very particular meaning of directly proportional. Super specific in the IB. The rest of this presentation, ladies and gents, there are some examples in trying to identify types of graphs and manipulating them. So I'm going to give you one example here on this slide, and the rest of the video is a practice problem, and I will talk about the answers in class. So here you can see this quick example, ladies and gents. I plugged in the data and it was very, very obvious that we were plugging in an equation where V, or volume, was inversely proportional to pressure. So I created that simple proportion. V is proportion to 1 over pressure. If I do know that this is the same as Y is equal to mx plus b, well, in this case, my m is just 1. My x is 1 over p. So by plugging those values in, modifying that data, I can create a new linear graph.